Hi, my name is Jordan Inyard, and I am presenting the laser-induced shockwave chromatography technique as my independent research project. When I first selected this technique, I was immediately drawn to its name, lasers and explosions. What's not to like about it? As soon as I heard of it, I quickly searched online so I could learn as much as I could, and I was not disappointed. During this presentation, I will discuss the potential of my chosen analytical technique. I will present the method in which it is currently used, its instrumentation, the type of analytes able to be separated by this technique, as well as future applications. The process of separation begins in the capillary, which is filled with a water and thermosensitive gel mix. Suspended in this mixture were fluorescence-labeled samples and the analytes. Once the capillary is filled, it is heated to 35 degrees Celsius to free the samples, making them ready to be irradiated by the laser. The analytes carried by the wave will stop at some distance from their initial positions by the viscous friction. Different particles experience different frictional forces due to the particle size and molecular weights. This change is detected by subtracting fluorescence images before and after the shockwave generation. The light and dark parts of the image correspond to the concentration of the analyte. This is used to construct the chromatogram by comparing the signal intensity with radial direction. The greatest advantage of the technique is its speed. The entire separation process takes only microseconds and is applicable to sticky and absorbing polymers as well as molecules as light as 7 kilodaltons. The system is based on a fluorescence imaging upright microscope equipped with a neodymium yttrium-doped aluminum garnet laser and a CCD camera. An objective lens under the sample stage of the microscope is used for laser irradiation. The examples shown in the report list the identities, masses, and travel distances of the analytes. All samples are organic animal-derived substances and show a general trend. The larger the mass of the analyte, the farther it will travel down the capillary. This relationship breaks down at around 300 kilodaltons, as the larger molecules tend to have many subunits that contribute to the friction experienced by the molecule. The upper limit of mass that the instrument was able to separate was approximately 10,000 kilodaltons. This novel technique in chromatography shows promise in aiding in the research of the nanoparticles and nanomolecules. From the research paper's test using animal proteins, it is suggested that this technique can be used in diagnostics of protein diseases such as Alzheimer's and Parkinson's disease. Improvements in the system can be readily made as the instrument does not suffer many limitations. The resolution of molecular weight recorded in the source paper was 28.5 kilodaltons. This could be improved by increasing the laser energy in a focused point by decreasing the inner diameter of the capillary and confining the sample. The chromatography is not limited to fluorescence detection, but is compatible with refractive index, Raman spectroscopy, radioactivity, and other techniques.